Well, here we are for the final of these 8 short lectures on hydrological data analysis and flood estimation for ungauged sites. Here we're looking at source of uncertainty and flood frequency estimation. And we're going to look at some of the source of uncertainty and think a little bit about how we might detect poor quality data. And remember this observed versus predicted plot from the previous lecture, where we developed a predictive equation involving catchment area and precipitation. And we find that despite our best efforts, a lot of the data do not lie very close to this one-to-one perfect prediction line. We're tending to over-predict the flood magnitude in small catchments and under-predict in larger catchments. Our black line here has quite low uncertainty, but it still left considerable uncertainty in our ability to predict values at an individual location. Remember too, the data were collected at different times. The SWS, BRS and Cagayan data have been collected at different time periods. Maybe climate has changed over the last 100 years. Land use and other conditions may have changed between when the SWS data were collected more than 100 years ago and our more recent data. How confident are we in the quality of the measurements made? We're dealing with data from 100 years ago. I'm sure it was collected very carefully, but are we totally confident in all of those measurements? Were they entirely reliable? We don't always know, but maybe some of the data aren't as reliable as we'd like them to be. What about human impact at the measurement sites as well? Remember, we talked about choosing measurement sites to be very stable, to be places where the river banks don't erode, where the bed is stable. It's possible, though, that there have been significant changes to some of the sites, and possibly the data show variability as a result of human activities. There are limitations in all of our catchment data. Our precipitation data a lot of it is interpolated from a relatively small number of sites and modelled. There's uncertainty in our land use data. We don't have detailed data, for example, on soil thickness and other properties that may be relevant. So there's always uncertainty in our input data there. And there's also uncertainty, we've mentioned about possible climate change. There's always uncertainty in whether any or all of these values that we're using may have changed through time. Are all of the relevant factors stationary? Do they have constant mean and variance? Are any of the changes that are in the data non-linear? If they're linear changes and they change progressively, we might be able to see that in the trends in the data. If they're non-linear, if there is major urbanization in the 1960s, for example, all happening in 4 or 5 years, we might not see that so easily in the data. We might detect something's happening, but we don't know quite what it is. We also need to think about how far in the future we wish to predict. If we want to predict the size of the 10-year flood that will apply for the next decade, maybe that's something we can do with reasonable confidence. But in 50 years' time, in 100 years' time, how much will the climate have changed? How much will mean rainfall have changed? How much will storm event rainfall have changed? So uncertainty gets greater the further into the future we attempt to predict change. We've also undertaken quite a lot of analysis on the data. And remember that the statistical methods that we've talked about assume that the data is stationary, that the mean is not changing, that the variability is not changing. The methods also are devised really for use with quite long data sets. Short data sets can produce bias. And I've shown an example here of a very short data set where the log Pearson 3 curve seems to go upwards. The Weibull curve seems to be the other way around. Curves can't do this. They they can't accelerate upwards as probabilities get less frequent. They go this way. And this is clear indication that because we've only got 4 data points, we really aren't able to describe the nature of that relationship terribly well. We have combined data from different data sets collected at different times. How valid is that? Are we really confident in what we've done? And we do need to carry out a bit more analysis just to check for the degree of overlap between the data and to reassure ourselves that what we've done is actually reliable. Whatever we do, though, our best predictive models at the moment still contain significant uncertainty, and there's always going to be some uncertainty in estimates of flood flows. The users of this information have to acknowledge that uncertainty. You can't pretend it's not there. You have to live with it and work with it and think about how it affects your decisions that you take based on the data that you've got. Just a couple of other things about these plots while we're here, though. The curves can't curve upwards towards the right, as I mentioned. Note, though, that the 30-day curves do appear a bit more reliable than the one-day ones. When you start to average out over a longer time period, you smooth out some of the variability that gives rise to these this poor fit to the curves. And actually, the 30-day curve here is not actually too bad at all. It could argue it's slightly better than the Weibull 30-day curve, which doesn't seem to fit the data perfectly well either. So uncertainty is absolutely crucial. We need to know where we may be generating uncertainty. We need to know, if not precisely how uncertain any of our estimates may be, we need to at least have an estimate of the confidence that we're going to put on those estimates. And we need to be able to communicate that to people who might use the estimates of flood magnitude that we are able to give them. Remember about the data set that we have. We've mentioned a few times that we've combined data from different sources. It's a good thing to do because combining data gives us a much larger data set overall. We have said a few times that we have strong confidence in our results because the data from different sources do overlap, which is very reassuring when you've got data collected by different people at different times. It's always good when the data seem to be consistent. The data handling side of it is very positive. The data use, I've mentioned that users must be aware of uncertainty. What else can we do to reduce uncertainty? Well, we might use information from other sources to help validate the statistical results. Maybe we can look at results from different locations. Maybe we can ask local people about flood levels. Maybe we can do some calculations using different methods, use some engineering hydraulics to supplement or complement our hydrology analysis. Think about other ways in which we can verify and validate the information that we've calculated. Remember the impact of climate change and that looking into the future becomes more uncertain. And remember too, something we mentioned in an earlier lecture, that someday the probable maximum flood might happen, or something very close to it. And when it does happen, we need to be able to survive. We need to be able to cope with it, to move people, to get them out of harm's way, to protect important infrastructure, to move animals out of the way of the flood, and so on. So we have to be able, at one extreme, to cope with the worst case condition. We can't engineer everything to cope with the probable maximum flood, nor can we engineer everything to cope with the worst possible interpretation of our results. Over-design of flood control is costly. It has negative impacts on people and the environment. And we need to think about alternatives. We need to use appropriate design. So we could turn all of our rivers. You've got some very nice rivers in the Philippines, very natural with diverse habitats, even in this case where you have a protected riverbank. You've got gravel bars, you've got shallow water, you've got deeper water, you've got vegetation growing in the channel along the side. You have a habitat that is worth conserving, as well as clean water and a river that changes dynamically. You don't want to do what they've done in this river in Brazil and turn it into a concrete channel. Sometimes you have to do that through the city, but it's not a great habitat. It doesn't work very well for people, animals, fish. You can't grow food in it. There's a lot of things you can't do with that, rivers like that. Occasionally, of course, you do have to engineer more substantially. You have to protect, in this case, protect a town from potential bank erosion. But the engineering must be appropriate, and it must be designed by taking into account what we know about flood magnitude and the uncertainty that remains in those assessments. And we must avoid expensive over-design based upon not properly understanding the data that we have. In the exercises that go along with the flood estimation part of the workshop, you will get to analyse some river flow time series, get to estimate the size of the floods of different recurrence intervals, and also get to try to estimate flood magnitude for a case where we don't have data, and compare that with some actual measurements from the same location. As you're doing that, at any time you might want to go back to one or more of these videos or just the PowerPoint presentations and have a look, remind yourself some of the points we've made. Of course, as we've said throughout, if you do have any questions, there's things you don't understand, please send us some the questions, and we'll do our best to answer them and to help you through the exercises.